So first things first, the name of the shape of a quadratic function is called a parabola. We know this, yes? Great. They're shaped like bowls or inverted bowls. So we have two parabolas on our screen. Our goal today is to talk about the characteristics of the two parabolas and be able to graph them by the end of class. The things I want us to know from the front here is that if the a value, meaning the value of the x squared term, is positive, that parabola is going to open upward, which is this first parabola here. It is opening upward. It is your happy parabola. It's a positive parabola. If that coefficient is negative, then the parabola opens downwards. That's your sad parabola. So our parabolas that open downwards look like frowny faces. That's our sad parabolas. So the first thing we need to know is whether it will open downwards or open upwards. And we get that information from the a value of the function. The second thing we need to know to be able to graph a parabola is the vertex. The vertex is the turning point of the parabola, either the lowest or the highest point. So we have a minimum value that's the vertex on the opens up graph, and we have a vertex that is a maximum point on the opens down graph. Does all this vocabulary sound familiar to us? Fabulous. The last piece of vocabulary we're going to identify here is called the axis of symmetry. The axis of symmetry is a vertical invisible line that the graph can be folded along to match each side to each other. This axis of symmetry does go through the vertex for either type of graph, and it's always invisible, meaning we know it's there, but it's not necessarily drawn on, but we can see it each time we graph a parabola. Does all this vocabulary sound familiar? Yay. That's all the things we needed to remember from Algebra 1. What we're going to be doing is taking two different forms of an equation for a quadratic function and using the characteristics to graph the function. So if you flip it open to the next page, we have the first type of function that's called vertex form. Vertex form is great because it straight up tells you the vertex in the exact equation. You don't have to do any sort of work to find the vertex. Vertex form of a quadratic equation is f of x equal to a times x minus h squared plus k. It gives you the recommendation that a cannot equal 0, and because then it would just be a line, because a being 0, everything would be multiplied by 0. This is vertex form. The important stuff here is that you find the vertex at the point h comma k. Just like we did for our circles, to find the center of the circle, h and k are the vertex, kind of like the starting point or the bottom top of the parabola, h and k. The parabola is symmetric to the line x equal to h, and that is your axis of symmetry, x equal to h. And just like we said on the other side, if that a value is positive, the parabola opens up, and if the a value is negative, the parabola opens down. So this one equation tells us a ton of information about the parabola. Yay, you're here.
I just not on it, but I made her go with me. I didn't think we were going to get stuck behind somebody.
Okay, grab a packet. So what we're going to do with vertex form is we're going to use vertex form to graph these functions. I've already worked out an example for you besides actually graphing it, but to show you the information that we need each time, here's our first example. Step 1, to determine whether the parabola opens downward or opens upward. So I looked at the equation and I saw that we have a -2 in the front. That means that we are going to have a parabola that opens downwards. So at the very end, our arrows should be facing downwards. Oh my gosh, that cricket is so annoying. Does anybody have eyes on the cricket yet? Oh, it's been driving me nuts all day. The vertex is found at the coordinate point 3, 8. Where did I get the numbers 3 and 8 from? H and K. Now, H is inside the parentheses, and notice that in the formula it says minus H, which means you're going to change the sign to get the number out, just like we did for the equations of circles. So that's positive 3 and positive 8 as the coordinates of the vertex. That's step 2. Found the vertex, H and K. Step 3 says to find the x-intercepts by solving f of x equal to 0. F of x equal to 0 means that I'm solving the quadratic equation in one of the various ways that we learn to solve quadratic equations in chapter 1. So if we see my work down here, I have my x-intercepts. I set the equation equal to 0. What did I do from the first step to the second? Moved over the 8. And then what? Something with the -2. I divided it by -2. And then what? Square root both sides. When you square root, don't forget you include plus or minus. Then what did I do? Plus 3 on both sides, which means I do 3 plus 2 and 3 minus 2. So my x-intercepts end up being x equal to 5 and x equal to 1. Step 4 says to find the y-intercept by computing f of 0. F of 0 means to plug in 0. So if you see me working this problem, I plug in 0 for every x. Then we just use PEMDAS to find the y-intercept. 0 minus 3 is -3. -3 squared is 9. 9 times -2 is -18. -18 plus 9 is not -10. LOL. It's because that should be a whole 8. Oopsies, typo. And then you get -10. I don't know why I changed that 8 to a 9 when I typed it, but you get me. Which means that we have a y-intercept at -10. If we put all of this information together on our graph and plot the vertex, the intercepts, and any additional points using the axis of symmetry, we can make a nice sketch of this function. Let's start with the vertex. We plot the vertex at 3, 8. So I go over 3 and up 8. There's my vertex. We'll make that blue. We have our x-intercepts at 5 and at 1. And we have a y-intercept at -10. Okay, the other thing I want you to do to make these graphs super accurate is I want you to draw the axis of symmetry in through your vertex, because it's going to allow us to plot 1 or 2 additional points very, very easily to make this a better sketch. The x-intercepts are parallel to each other, are symmetrical to each other. From the first x-intercept, it takes me 2 jumps to get to the axis of symmetry. So 2 jumps away, there's the other one. The y-intercept is 1, 2, 3 jumps away from the axis of symmetry. So where do I plot another point? 3 more points the other way. 1, 2, 3. There should be another point right here. So doing that again, so you can see it live. This is 1, 2, 3 jumps away from the axis of symmetry. So I go 1, 2, 3 jumps away from the axis of symmetry to plot another coordinate point. Once you have nice, neat points, probably about 5 of them is usually enough. We're going to play connect the dots and draw our parabola. And boom, we have a nice, neat graph function. Yeah. Don't judge my nice and neat graph, okay? It's better than the circle.
I don't know. I think the circle might have been better.
All right. I don't need a sort of negativity. Can I have you guys try one? Yes. All right. This next one is for you. I want you to follow the same steps. So you're going to find whether it opens up or down, find the vertex from vertex form, give me the x-intercepts, and give me the y-intercepts. Okay, so I started working this problem out and I realized that I should probably say something. So a is greater than 0 here, it opens up because it's +1 there. We have a vertex at -3, 1. Did we do that part right? Yes, a question. Thank you so much for asking. Normally, this should say minus a number, right? In the formula at the very top of the page, it says -h. So if you see plus a number, you know you plugged in a negative number because minus a minus is plus. So it's like basically it's the opposite number. Okay, and then I started finding the x-intercept, actually writing it down correctly this time. So you subtract 1 to the other side. When you take the square root of -1 though, what do you get? plus or minus I, because the square root of negative 1 is I. If we keep solving this, this ends up being negative 3 plus I and negative 3 minus I. My question for you is, how do you plot negative 3 plus I, negative 3 minus I? Like, where would I put that on this number line? I'm so glad that it's crickets chirping, not actual crickets chirping, but you know what I mean. No silence. You can't plot it. The moment it's imaginary, that means it's not actually going to cross your x-axis.
Since it's upward, will you do it with the y-intercept, the 3 away from the y-intercept?
Basically, yeah. So what we'll do to find the y-intercept here, right, we plug in f of 0, which means we're doing 0 plus 3 squared plus 1, which is 3 squared plus 1, which is 9 plus 1, which is 10. So here's the things I have here. I have that we have a vertex at negative 3 comma 1. I have a y-intercept, I used the wrong color. I have a y-intercept at 10. And I know that there is an axis of symmetry that goes through that vertex. So I can find nice, neat points by reflecting any points I have. In this case, it's just one other point onto the other side. 1, 2, 3, 1, 2, 3. And then without judging my ability to draw a curve, we're going to draw a nice parabola through here. Were we on the right track even if we didn't get it right? So one more time, why did we not graph any x-intercepts? They're imaginary. You don't plot imaginary things on a real number line. And we're dealing with a real number line. Very cool. Also, if you think back to when we did this in like Algebra 1, if I showed you this picture and asked what are the solutions, you'd say there are no real solutions because it doesn't cross the x-axis at all. So all of that kind of makes sense and it goes together. How are we feeling? Good. Can we see another type of quadratic equation? Thank you for your honesty. We're going to do it anyways. This is vertex form. I love vertex form. It tells you a lot of information. But the version of a formula that you've probably seen the most is called standard form. Standard form of an equation is alphabetical order with the ABCs. This is probably what you're used to seeing when it comes to quadratics. Yes? Unfortunately, this doesn't tell us a lot of information about the graph to help us graph it. So we have to do a little bit of work to find the vertex so that we can do everything we did on the other side of this paper. The vertex from standard form is found by doing negative b over 2a, comma f of negative b over 2a, which looks really complicated. All we have to do is figure out what this number is and then plug it into the function. That's all this says to find our coordinate. Other than that, the steps are all the same. We determine whether it opens up or down. We find that fancy vertex. We do the x-intercepts, we do the y-intercepts, we plot all of the things. So other than having to work a little bit harder to find this vertex, we're doing the exact same thing about whether it opens up or down. We're finding the x-intercepts and y-intercepts and then using that axis of symmetry to connect the points. Can we do that? Let's graph this one. So we're graphing the equation f of x equal to negative x squared minus 2x plus 1. Then we're going to go on to graph or to state the function's domain and range. All right. The a value here still contains the information about whether it opens up or opens down. Does this one open up or open down? Down. Since a is less than 0, it's a negative number, we're going to open down. Now finding the vertex takes a little bit of work. To find the vertex, I first need to find out what negative b over 2a is. All right, we're going to do negative 2 over 2 times negative 1. Do we know where I got all those numbers from? Ed Sheeran is kind of loud today. Do we know where the b comes from? Yes. Yeah. ABC order, so b is negative 2. A is negative 1. So negative b over 2a. Negative 2 is positive 2. over 2 times negative 1. So that ends up being 2 over negative 2, which is negative 1. So the first coordinate of my vertex is negative 1. To find the second value of my vertex, all I'm going to do is plug in negative 1 to the function, which means I'm doing negative negative 1 squared minus 2 times negative 1 plus 1. This is negative 1 plus 2 plus 1, which is 2. And oh my gosh, all of that work to tell us that the vertex is the coordinate point negative 1 comma 2. It was much easier in vertex form. We just looked at the numbers. In standard form, we can't just look at the numbers. We have to compute the vertex. I went really fast through that. So can someone ask me a question? So I did negative b over 2a. We followed, yes? We took this number and we plugged it into the function. This is me plugging it in. We got 2. So my coordinate point for my vertex is negative 1, comma 2. This is negative b over 2a. This is f of negative b over 2a. After this, what we need to do is we need to find the x-intercepts and the y-intercepts. The x-intercepts are found whenever we set the function equal to 0. So we're going to say negative x squared minus 2x plus 1 equal to 0. Now, if I'm working on this one and I want to factor this, which is usually how we start solving a quadratic, this shaped like this is a trinomial, I'm going to switch all the signs because I want the x squared term to be positive. And after lunch, we'll pick this back up. All right, I kind of forgot what we were doing before lunch, so let's just start it on over. So we were finding the x-intercept. To find the x-intercept, we need to solve this quadratic, and since this quadratic is in standard... Yeah, in the bucket. Since it is in standard form, we're going to want to try to factor it. So we divide by negative 1 everywhere, basically change the sign so that x squared is positive. And then we think to ourselves, are there any numbers that multiply to negative 1 and add to positive 2? Like if we were going to factor this. What would work? We want to find numbers that would multiply to negative 1 and add to positive 2. One and negative 1. Okay, I see what you mean because 1 and negative 1 make positive, or sorry, negative 1 when we multiply. But when I add those, do I get positive 2? Oh, no. Guess what? This is not factorable. So in fact, we're not even going to do this process. We have to use a different tool to solve this quadratic. I recommend using the quadratic formula just because it is a one-stop wonder for getting this done. So we're going to do x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And just because we're using this to plot functions, we're going to go ahead and just get a decimal approximation here. So we would throw all of that into a calculator. And we're going to fast forward through that part because we've done that in a previous chapter. We would get that x is approximately equal to negative 2.4 and 0.4, which are our two x-intercepts. Okay. Thinking back to what we were doing, again, started this before lunch. We found that it opens down. We found the vertex. We have the x-intercepts. We need the y-intercepts. Remember, we find the y-intercepts by plugging in 0 to the original function. So we're doing a 0, negative 0 squared minus 2 times 0 plus 1, which is just 1. All right, that's the ton of information that we need to be able to plot this parabola. So we start at the beginning. We have a vertex of negative 1 comma 2. we have x-intercepts at approximately negative 2.4 and 0.4. And we have a y-intercept of 1. Now again, we can use that axis of symmetry line to find a few more points to make this a nice, neat graph. So 1, the y-intercept would reflect to negative 2, 1. And that's probably good enough to make a nice, neat parabola. And this checks out because it opens down, which we said it should. So the steps are still the same from when we're in vertex form and standard form. Standard form just requires a bit more work in finding the vertex. And potentially every single one of these could have a different method to solve for the x-intercept, but the quadratic formula works every time in standard form, so this might be pretty helpful to use if we just get really good at doing the quadratic formula, especially since we just need a decimal approximation to plot the point. Sound good? The last bit of information here is kind of a shortcut for your brain to take. If I'm asking you to find the maximum and minimum values of a quadratic function from standard form, we know that if a is positive, meaning it opens upward, that means that the parabola is a happy-looking parabola. A happy-looking parabola is going to have a minimum function, or a minimum for that function. And it occurs at that vertex, negative b over 2a, and the minimum value is evaluated there. However, if it's a sad parabola, meaning that it opens downward or a is less than 0, our sad parabolas are the ones that have maximum values. But that occurs at the vertex. So it's just really easy. Just looking at an equation, you can tell whether it will have a maximum or a minimum, and it all depends on that a value, the first number in front of x squared. So the value of x gives the location, and the value of y gives the maximum or minimum value itself.